Live. Okay. So, quick overview of this course based on a little of the previous one. Calculus 1 solved the problem about the rate of change of a function. Was the big problem we solved, and then we look at different ways to apply that. So rate of change, that's what we call the derivative. That was that limit as h went to 0 of f of x plus h minus f of x all over h, which you guys all learned to grow and love. Something like that. No one loves. There we go.
What about?
And then the bottom line is, in order to have a derivative of the function, this is what it means to take a derivative, but we found there were shortcuts. So we didn't have to do that all the time. We saw patterns. Okay. So calculus 2, on the other hand, the big problem there is area. And there's a lot of applications to area. Sometimes areas are pretty easy to find. Like, for example, my pen's disappeared. There you go. My pens. Oh, there they are. Okay. So, for example, suppose we had a graph that looks something like this. And these are horizontal lines. Would you agree that we could find all those areas pretty darn easy once we knew the scale? Right? It's just length times width. So those areas are easy to find. However, this area would be harder to find. Agreed?
Yeah.
Like, what is that? Is it parabola? Is it something else? So our goal is to be able to find this kind of area. And that's what calculus 2 is all about. This idea of finding areas is called integration. And it turns out, and this is the beautiful thing that was discovered by, who do you think invented calculus? Anybody know? I've talked about this before. Isaac Newton is attributed to inventing calculus. Another guy named Leibniz was also did it independently around the same time. They didn't actually invent all of calculus. Calculus had existed for hundreds of years before that. What they did is they got a better grasp of it, and they found these two areas of calculus were connected to each other. And so that's one of the big things we're going to get into in chapter 1 is how derivatives and integrals are related to each other. How finding the slope of a function is related to finding the area of the function. And their relationship is kind of like how multiplication and division are related to each other. So that's an overview. So like when we did derivatives, the first thing we had to do is figure out what the derivative was. Once we did that, we had to come up with all these formulas. Then we figured out how to use derivatives in different contexts. Then we found out how to do harder problems. This class is exactly the same, but with integration. We learned what integration means. Basically, we developed some formulas and patterns for it. Then we learned how to apply it in different areas. And then we learned how to do harder problems. That's chapters 1, 2, and 3. Basics, applications, harder problems. Okay? So, I'll come back to these two problems. So a little warm up from before. You guys are all really good at derivatives, right? Right? Sure. Thank you. You passed last term. You're really good at derivatives. Derivatives. So what I'd like to do is get a list of some derivative formulas we discovered last term. Okay? Not the definition of the derivative at the limit, just the shortcut formulas. So can somebody think of a common formula from last term?
Product.
The product rule was one. Yeah. So if we took the derivative with respect to x of f of x times g of x. Anybody recall what that was equal to?
Times g prime of x.
F
Of x times g prime.
times g prime plus
F prime.
F prime
F
times G.
times G. So basically you hold one function still, take the other derivative, then you switch. And it doesn't matter how many functions are in the list, that's the way it goes. So even if there are 3 or 4, we can still do it. You just take the derivative of one function at a time, is what we discovered.
Quotient.
Quotient rule is another big one. Derivative with respect to x of f of x over g of x. Looks pretty similar to this, but you got to start with f prime first. Minus, right? F times g prime. And the key is the minus has to go with the derivative of the denominator. And then all over
Low squared.
low squared, denominator squared. Yeah. Those were 2 big ones. What are the rules?
Quotient rule.
Not
quotient, chain rule.
Chain rule, sine and cosine. Yeah, we got a ton of
My
these. So I'm not going to list every single one. I'm just going to list some. So let's list the chain rule, then we'll list some other special ones. If you compose 2 functions, f of g of x, then you get f prime of whatever happened to be there, the g, then you have to adjust by multiplying by the derivative of g of x, g prime there. Now, those are some big formulas. Other ones, derivative of the sine,
1 over.
It's just cosine.
just the cosine.
Oh, that's part of
Derivative of the cosine,
Negative.
negative sine. Let's see, somebody had mentioned arc functions, derivative with respect to x of, does anybody recall the arc sine?
1 over the square root of
1 minus squared.
x squared.
No, 1 minus.
1 minus x.
Yeah, that is correct. And how is the arc cosine related to this?
It's just negative.
Just the opposite of it, yeah. Okay, so that was a useful one. How about some others? How about the power rule? Remember that one?
And
Oh.
The derivative with respect to x of some power of x, like x to the
And
23rd.
23x
to the
22nd.
All right, we dropped the power by 1, and we wrote that with an n in there before instead. So derivative with respect to x of x to the n would be n times x to the n minus 1. So we've listed quite a lot of rules. There were others. Here's another important one. The derivative with respect to x of the natural log of x.
Oh, I know this one.
What is
1
it?
over x.
1 over x. Good. How about e to the x? So slightly harder version of that. What's the derivative with respect to x of 2 to the x?
Oh wait, no. X goes onto the bottom, -1, right? Can you do that?
Not negative.
No, you can't.
X e.
is it?
And 1 over, right? Isn't it 1 over?
It's
You
the
have to make it a log.
logarithm.
It's 2 times x to the -1.
No. It's the logarithm, isn't it? Yeah.
Isn't it 1 over?
It's the natural log of 2 times 2 to the x.
We did.
And that actually applies to e. Does anybody know what the natural log of e is?
1.
It's 1, so it doesn't change it. Yeah, if the base isn't e, you have to adjust by multiplying by the natural log of the base. I went over a proof of it. I'm not going to do it again.
Okay.
That's something you just need to know.
I'm sure I don't.
All right. That's not every derivative formula, but it's a lot of them. Now, at the end of Calculus 1, we looked at antiderivatives. Meaning, if I tell you what the answer is, can you tell me what function we took the derivative of? Okay, so that's the idea of an antiderivative. So the question there would be something like f prime of x is equal to 3x squared. What did f of x equal?
3 half x to the cubed.
1/3 times 3.
Write something down. Don't just think out loud.
1.
It would just be x cubed. Yeah.
Oh.
Because you can check by taking the derivative.
Plus some constant.
Plus some constant, like I was thinking plus pi. But it could be plus anything, even plus 0. Yeah. So when we take a derivative, we lose track of information sometimes. So recall that the derivative with respect to x of any constant, like 5, is 0. So if there was a constant added onto the function, we lost track of it. Right? So in antiderivatives, often we'd want what's called a general antiderivative. So that means, for example, if I said f of x was equal to 3x squared, or f prime, excuse me, then f of x, the general antiderivative would be 3x squared plus c. C is just some constant.
Oh, shit,
Oh shit, it would be x cubed. Sorry, I don't know why I did that. Brain fart. And sometimes that constant could be 5, or it could be pi, or it could be 0. We just don't know. And so we would need some other information to try and figure out which specific function had that derivative. Because there's a whole bunch of them that have that derivative. All right, and it turns out antiderivatives are going to be helpful when we're working later with some harder integration problems. All right, so there's a review on antiderivatives, which is going to help you guys brush up on remembering your derivative formulas, which is going to be more useful later. So that is your first homework assignment. Some people already got it done. If you didn't, try to get it done today. We are going to take a look at an area problem. And I'm going to combine this with another idea, speed versus distance. So we're kind of familiar with the idea that distance is equal to speed times time. Okay, we talked about that. That was an application of the derivative previously. So I was walking to and from school the other day just for fun. It was such a beautiful day. So time and speed on this axis. And sometimes I walked pretty fast, and sometimes I'm lost in thought, thinking about calculus, and I slow down a little bit when I'm walking. So for some of my walk, I was walking fast, some of it I was walking slow. So 5, 10, 15, 20, 25, 30. So it takes me about a half an hour to walk to school. So here's time in minutes on that axis. Speed, 1, 2, 3, 4, 5. And this would be miles per hour. When I'm thinking about getting somewhere, I walk pretty fast. So let's say about 5 miles per hour. If I'm walking uphill, I'm probably going to slow down a little bit, maybe 3 miles per hour. If I'm just on flat ground, I'm not worried about speed too much. I walk faster than probably the average person, even about 4 miles per hour. So let's say that for the first 5 minutes of my walk, I was walking 5 miles per hour. Maybe I'm going downhill from my house. Excited to get to work. Then I hit the flats, and I'm still cruising along, but I'm just going to go 4 miles per hour for a little while. So let's say for the next 15 minutes, I'm going 4 miles per hour. And then for the last 10 minutes, I got to slug it up the hill to the college.
Wait,
Maybe I'm slowing
15.
down. What's that? To 3 miles per hour while I'm cruising up that hill to the college. So this is what my graph would look like if you were tracking my speed. Right? Maybe I map my walk running on my phone. It's keeping track of my average speed as I'm hustling these different spots. If I know the distance of the speed here, right? So in this rectangle, the first one, I'm doing a constant 5 miles per hour. we're all familiar with the distance is equal to speed times time. So my distance there would be my 5 miles per hour times the number of hours that I was doing that. Well, I was doing it for 5 minutes. That would be 5 out of 60 for hours. So what's the result of that calculation right there? 5 times 5 is 25, whatever 25 over 60 is. Could be reduced, some of it being 5/12. Yeah. Which is a little under half a mile. Is that right? Yeah, 6/12 would be a half. And notice the hours would cancel here, leaving the units as miles. Remember, unit analysis is sometimes important when we're doing that. So for the first 5 minutes, I covered about half a mile. And then I slowed down in the flat area here, but we can still calculate that. Let's do color there. So what's the, and again, aren't I doing area, right? I'm taking the height of this rectangle, and which is my speed, and I'm multiplying by the length of the interval, which is time in this case, which also happens to be distance equals rate times time. So in this red one here, I have 4 miles per hour times 15 minutes, 1/4 of an hour. So that means I've covered 1 mile in that chunk of my adventure. And then for the next chunk of my adventure, I need this area over here, so I need the length and the height there. So what do we have there? I'm going 3 miles per hour times 1/6 of an hour, right? 10 minutes in an hour. Somebody nod and smile, please. Okay, thank you, Rob. Times 1/6. And let's see, one's would be half a mile. So according to this, if I know the speeds I was traveling at each point, then I can say, well, then the total distance here is just the sum of those areas. So I've got 5/12 of a mile plus 1 mile plus 1/2 of a mile. Which gives me what? Almost 2 miles, 1 and 11/12. So almost 2 mile walk. So just review speed. What is speed? How do we find speed?
So, yes.
But in general, how do we find speed?
Derivative.
It's a derivative, yeah. It's distance over time, it's a derivative, yeah. So what I've done here is I have the derivative of me walking, and I took that derivative and I turned it into a distance. That distance graphically is an area, and an area is an integral. So I just turned a derivative into an integral here. This idea is called the fundamental theorem of calculus. We'll spend more time on that next week. For now, we're just going to try and find areas. Easiest kind of area for us to find is rectangle, right? Base times height. If it's not a rectangle, we have some work cut out for us. So let's look at a more challenging problem. Let's take just our friendly old basic parabola. We're going to graph this sucker. We have a point at 0, 0. We have a point at 1, 1. We have a point at 2, 4. And let's see, can I fit 3, 9 on here? 4, 5, 6, 7, 8, 9. There somewhere-ish. It's a little shallower at the bottom here, and then it gets steeper as we head out, and then there's this mirror image on the other side, right? Suppose I wanted to find the area up to where this function gets to 3. So I want to figure out what is this area right here. it's almost a triangle, but that curved side, is a problem. And I'm thinking back to geometry I've had before. We learned about rectangle areas and triangle areas, even the area of a circle. But area of a parabola, that didn't come up in my geometry class. Okay, so and that's the role of calculus. If the curve is something other than a circle or a straight line, that's when we need calculus. So we can approximate this area, and the way we're going to do that is by saying, well, I know I have the point, oops, that's my pen. I know I have the point 1, 1. Right there. So I could say, I could just say, let's just use that rectangle as an approximation of the area. And then I could come over here and say, well, I know I have the point 2, 4. So I could just say, well, let's use that rectangle as approximation of the area. And then the same thing over here, I know I have the point 3, 9. So I can just turn it into a bunch of rectangles. That's a bit of an overestimate, right? Because we have some chunks of these rectangles that are outside of the area I'm interested in. But that simplifies this problem greatly. So I could say that the area here is approximately a 1 by 1 rectangle plus a 1 by 4 rectangle plus a 1 by 9 rectangle. And if I add that up, I get, on a good day, 14. Okay, and that's an overestimate. I could do an underestimate of this using a similar process. So I'm just going to draw a little picture of that over here. So there's my function. My underestimate at 1, 2, and 3, instead of grabbing the right endpoint over here, I could grab the left one. Yeah, so I could say, let's grab the left endpoint. Ooh, that's a nice rectangle. It's 0 in height. Then the next one would be 1 in height, and the next one would be 4 in height there. Okay. So in this case right here, I'm grabbing left endpoints. In this side over here, I was going for right endpoints. Will right endpoints always yield bigger areas than I need? Answer is it depends on how the curve is shaped. It depends, not always. This right endpoint happened to be what we call an upper estimate. Sometimes it's called an upper sum because we're adding things up, right? And guess what the left endpoint would be called then? Oh, lower sum or lower estimate. So this could also be called a lower estimate or a lower sum. And sometimes in the homework problems, they'll say, hey, approximate this area using left endpoints. Sometimes it'll say using right endpoints. Sometimes it'll say upper sum or lower sum, right? In which case you have to make some decisions as you go to try and solve the problem. So let's see, what would the lower sum here be anyway? It would be 1 times 0 plus 1 times 1. Plus 1 times, we're evaluating there at, it's going to be 1 times 4. So then the lower estimate here is 5. So the actual area is somewhere between 14 and 5. Anybody see how I could use those two numbers to get a better answer?
Yeah.
I can just average the two of them. Yeah. And averaging the two of them is going to be kind of like making little triangles out of these things instead, trapezoids out of them. So I could average those. So 5 and 14 is 19. And that's, yeah, so it'd be about 9.5 would be a better estimate of the area. So we can average the left endpoint sum and the right endpoint sum. Other ways we can get a better answer here, use more rectangles. I only use 3. Instead of going every 1 unit, I could go every half a unit. So let's just do that for fun. So we have 1, 1. We have 2, 1, 2, 3, 4. 4 would be there. 5, 6, 7, 8, 9 would be somewhere up there. So there's my crude sketch, parabola. So I could say every half a unit, I could make a rectangle, and you could go for left or right. Let's say I want to go with right endpoints. So then my area would look more like this. And I'm going to have to figure out what each of those function values is. So I'm going to make a table to help me do that. I'm going to need to know the x value, and I'm going to know what the y value is. These little distances right there, I'm going to call those a change in x, delta x. Remember we used that notation sometimes last term? Sometimes we called it h. We could call it h too if we want. So my delta x in this case is 1/2. That's the base of each rectangle. So the first x value I'm going to plug in is 1/2. The next one is 1, then 1.5, 2, 2.5, 3 are the endpoints I'm going to use. If I was using left endpoints, what x value would I start at instead?
3.
Zero.
Left, I would start at 0, and I wouldn't quite get to 3 because the left endpoint on the last one would be 2.5, right? Okay, so it would be a little different. And then I just have to figure out what's the y value. So that means I just square each of these. So this is going to be 0.25, 1. Let's see, 1.5 squared I think is 2.25. 2 squared is 4. 2.5 squared I think is 6.25?
Yeah.
I didn't do that in my head, I just remember it. And then 9. So I'm just going to continue my table, because then those are the f of x, those are the heights of each of my rectangles, right? What's the width of each rectangle? It's always 1/2. Yeah, so now I'm going to just find my little rectangle areas by just multiplying each of those numbers by 1/2, and then I add them all up, right? So here I'm going to have 1/2 of a quarter, which would be 1/8. I'm going to need maybe some help with the calculator here. 1/2 of 1 is 0.5. 1/2 of 2.25 is 1.125. 1/2 of 4, I got that one. That's 2. 1/2 of 6.25 is 3.125. Yeah, thank you.
Wait.
1/2 of 9 is 3.5.
Wouldn't 1 and 1/2 wouldn't 1 and 1/2 times 2.25 be 1/2 of 2.25 plus 2.25? 1 and 1/2 times
Just did it.
2.25 should be bigger than.
No, it shouldn't. Because you're
Which
not times
step?
by
No,
1.
no. I'm not multiplying these two together.
They're just multiplied by 1/2.
These I'm all multiplying by 1/2. So each of these function values is the
okay, I
height,
was so
but the
confused.
width of every
Okay.
single rectangle is 1/2. I'm not multiplying by the x value.
Okay.
Half of 9 is 4.
Yeah, so what I'm doing for each of these, I'm taking the function value and I'm multiplying that function value every time by delta x.
Mhm.
So every time I'm just multiplying by 1/2.
Okay.
In the previous example, I multiplied by 1 all the time. And then anybody ever use a spreadsheet in here?
Yeah.
Okay, you know the button to get a function to happen?
Uh-huh.
It looks like a little funky SE kind of thing. That's the capital Greek sigma. That means to sum things up. So you're going to see that notation a lot starting today.
Lovely.
So in this red column over here, I have a list of the y value times the width of the interval. The next thing I need to do is add all of those up. And that's going to be my approximation of the area here. So let's see, 5, 5, and 5.
1/2 of 9 is not.
1/2 of 9 is not 3.5, it's 4.5. Good job. Somebody's paying attention. All right, carry the 1, 2, 4, 6. I think that's going to be a 7 next. 1, 6, 7, 8, 13. Am I doing this right? Carry the 1. 9.375. No? That's not what you got? Did you get something close to that?
5.
11.375? Okay, that's could be, I can't. Oh, I forgot the 2, 9, 10, 11. You're right. Thank you so much, Henry. Keeping me straight. 11.375 is that estimate. Is this an overestimate or an underestimate?
Over.
It's an overestimate, yeah, and usually you gotta draw the picture to see that. So this would also be called an upper sum, because it's every rectangle is an overestimate. William, what's up?
Oh, never mind. 3.5.
Yeah, I messed that up earlier. Yeah, it's 4.5. Yeah, so that would be the estimate of the upper sum. Similarly, we could do a lower sum, a left endpoint sum. And the cool thing about that is we already have like most of the work here for that. So what's the difference? If I did a left-hand sum, I would have had to start at 0. And then I would plug in a half.
3, don't you?
So for a left endpoint, I would plug in 0, a half, 1, 1.5,
You don't have the.
2, 2.5, but I'm done at 2.5. I don't have to plug in 3.
Yeah.
Yeah, so a left endpoint sum would just be here up, but I'd also need to know what is f of 0. Well, it happens to be 0. Yeah. So the lower estimate here would just be these guys right there. So sometimes when you do a left-hand sum in a table, you almost have everything you need for the right-hand sum, or vice versa. You just have to do a tiny little bit of work more. And so that's an interesting thing to know. So let's see. So the left sum would be what here? So this one's the right sum. If we chose to do a left sum, it would just be what, 4.5 less than that? Somebody help me out with calculators.
6.875.
6.875. And given those two numbers, how can I give an even better estimate? Average the two of them together. Yeah, if we average the two of those together, we'll get even closer to the actual sum. Okay, so this method right here, where we keep making smaller and smaller widths for the rectangles, so next we could do maybe a 10. We could do 100. Would you agree this is starting to get tedious by hand?
Yes.
And we would like a spreadsheet or some other computer system to help us?
Yes.
A spreadsheet can whip this out really easy, right? Just a couple of columns on a spreadsheet, fill down, because it's the same steps every time. But there's also programs that do this for you. Okay. I'm going to hold off on showing you that till tomorrow, though.
Yeah, 3
Yeah,
minutes.
Rob Lester.
So that's
But we
for
stopped
the
before.
portion of the function that's increasing.
Yeah, so if it's a part that's decreasing, yeah, then it's going to look different. So just quick note on that. Let's suppose we were interested in this side of the function over there. So we have -1, we have -2, we have -3. The y values are still 1, 4, and 9. If I were going to do, let's see, what did we start with before? Right-hand endpoints. My right-hand endpoints would be color. 0 would be the right endpoint of this interval. -1 would be the right endpoint of this interval. And -2 would be the right endpoint of that
So it means
interval.
we switch to negative.
So this is what's called a right sum. But in this case, because it's decreasing, the right sum is a lower sum. Oh, a lower sum. Yeah, and if the function that you're looking at switches from increasing to decreasing, then some of the time it's an upper sum and some of the time it's a lower sum, even if you stick with right endpoints. Like another example, let's suppose we're looking at f of x equals the sine of x on the interval from 0 to pi. So here's 0, let's say we put pi right there, right in between is pi over 2. The sine starts at 0, 0, right? And then it peaks at 1 at pi over 2, and then it drops down to 0 again at pi. So this would be a graph of the sine on that interval. Let's say we split it up into 4 subintervals, which means we would go every pi over 4. So this would be pi over 4. 2 pi over 4 would be pi over 2, and then this would be 3 pi over 4. And let's say we go with right endpoints again. So let's find a right sum. So we'd evaluate first at pi over 4, which gives me that rectangle. Then I'm going to evaluate at pi over 2, which gives me that rectangle. Then we evaluate at 3 pi over 4, which gives me that rectangle. And then evaluating at pi gives me that very lovely flat rectangle. It's just a line. So the right sum on one part of this is a lower sum, on the other part is an upper sum. Sorry, upper sum and then lower sum over there.
Would it be better just to do an upper sum?
So
Or is it easy to do
it
that?
depends, right? So one nice thing about here, I'm overestimating on one side and I'm underestimating on the other side.
So they
Do they
average out.
balance out perfectly? No, they don't. But it's kind of nice that that happened. Okay. So the point is, you just have to consider what you're doing each time, right? It's easier to program a computer to do a right sum because you always just grab the right endpoint. If you're programming to do an upper sum, all of a sudden you have a decision to make at every point. Oh, do I go this way or that way? That make sense? It's a little trickier to compute, right? So in which case software is going to be helpful for us to do that. All right, so we got another day or two on this section. This is one of the harder sections because there's got a lot of stuff in it. I need to talk more about these sums, in particular using this notation, because it does get more interesting because we're going to throw some more parameters on that. Okay. So check out the videos, try the homework, read the book. For sure you want to do that review section on antiderivatives and then jump into this as soon as possible. That's it for now.